So, ultra brief recap of what I did last week for almost all of you who weren't there. Right, I described sort of generally moduli spaces of pseudoholomorphic curves as, well, compact spaces, which we get from, well, first of all, taking pseudoholomorphic maps, quotienting by reparameterizations with automorphisms of the domain, and then, well, not quite compactifying it, but adding broken and nodal curves so that afterwards it is a compact set. So it's lovingly called Gromov compactification. And there are cases, I think, where there simply are no not nodal curves in a certain moduli space. So this quotient, this is not necessarily dense in the M bar. And the good news here is that the space of holomorphic maps is the zero set of a Fredholm section. Roughly speaking, there's a Banach bundle where the base curly B is some Sobolev space, some Sobolev completion of maps from domains. Where, you know, both the domains and the targets could also vary along with the maps. So that was that's the good news in terms of description. And then the first piece of bad news is that this the quotient by the automorphism group here is a quotient but that of something that, at least on the level of this Banach manifold, is a nowhere differentiable action. So, you know, how are you going to take that quotient? Well, again, there's a piece of good news. This quotient as a topological space actually has local slices that are, you know, homeomorphic to Banach spaces, and that's where we use sort of geometry to construct them. Right, so we use sort of intersections with hypersurfaces to fix the parameterization. And so then we can then use these local slices to get, you know, a local description of this. This is M twiddle mod out also. Right, the sort of non-nodal part of the moduli space we can locally describe as the zero set of the d-bar operator over the local slices that we got by geometry. So far so good. And what I was going to claim very quickly, and you know, we'll see more of that, is that we also have local Fredholm descriptions, at least within this set of broken and nodal curves. So that's because these broken and nodal curves we can think of as or the set of broken and nodal curves you can think of as a fiber product of, you know, depending on how often it breaks, or nodes will have several copies of zero sets of d-bar operators, mod automorphisms.
So can I just orient myself?
Sure.
So
Most
sigma
definitely.
is no boundary, no mod points on honest thing, or how do you want to?
Well, so right. So there are two ways of thinking about this. One way is to think of the model case. Sigma is just the sphere with a marked point at infinity. M is going to be a compact symplectic manifold. What I argued sometime last week is that pretty much every moduli space of pseudoholomorphic curves has roughly this structure, right? So sigma chi might have boundary, there might be marked points, there might be a whole like Dillon-Mumford moduli space of complex structures to deal with on sigma.
I see. Okay, so when you write del bar J inverse of 0, that J could actually be dependent on something.
It could be dependent, right? I haven't put little j in here, so so this is sort of a very rough form. There's a 0 set of a Cauchy-Riemann operator, and that might depend on many parameters. Yeah, but so if you get confused in these things, just think of pseudoholomorphic spheres. Yeah.
And I'm also confused because so B is just a Sobolev. You haven't given it a Fréchet structure or anything to space B, so I don't know what you mean by nowhere differentiable. Like,
oh well, if it's so okay, so this would then be a Banach manifold. In particular, Fréchet.
Okay, got it.
Yeah, sorry. And of course, that's not that is not entirely trivial. That you can make that base space a Banach manifold.
Are there different ways of making it Banach that give a different Fréchet structure?
Oh yeah, I mean you can take whichever Sobolev completion you'd like, right? And I think they're all different.
And you're claiming it's no matter which one you take, it's going to be nowhere differentiable.
Here, yes, I pretty much C, K, W, K, P. What I don't know of anything that will do the job. Right, if you want the smooth maps to actually lie within it.
I see.
Okay. If you allow yourself to, that's something that Fleur did, I believe, and I haven't checked that. There is a Banach space of smooth maps, that Fleur constructed to make perturbations at some point. That might be a neat exercise to check whether reparameterizations act smoothly on that. They might, but that doesn't really help us because at the end of the day we want to, we want our moduli space to be big enough that it contains all the pseudoholomorphic curves we care about, and we can't be sure that it would lie within the sort of Fleur smooth maps. Good. So with this, we'd have sort of at least local nice Fredholm description for this quotient set, and also nice Fredholm description for the sort of nodal part here. We haven't said at all how these sort of tie together. Yeah. Whether they're I'd like this to be a connected space, and so on the whole compact set, I would now like to make a topology in which is actually compact and in which the two components get connected. So that's the topic of gluing that we need to look at next. There we go. So for this, I think the main reference and sort of easiest to get through is Salomon's lecture notes on flowmology. Yeah, they're sketchy, but the gaps are fillable. They also become wrong towards the end, so I think section 5 or 6 you don't want to look at. And this message is authorized by Dietmar Salomon. But section 3 is still perfectly fine. The end is sort of where he wants to you go into multi-valued perturbations and trying to deal with sphere bubbles. And there's a much more extensive discussion of gluing in the big, and actually all McDuff-Solomon books on J-curves. It's just that the Flow-homology cases, you're gluing cylinders, and that's actually easier to deal with than the case of spheres. So Wolfgang can report on that. However, if you're looking at the lecture notes on Flow-homology and you're getting to places where there's obvious gaps, you can probably go to the J-curves book and find how one really technically rigorously deals with that. So let's see. Right, so first, as promised, in what sense are these broken or nodal curves actually fiber products? Right. So I haven't, strictly speaking, defined the Hamiltonian flow trajectory spaces, but I guess I did that last semester, so I'm just going to fly with this. So here I want to fix a positive end gamma plus, a negative end gamma minus, and I'm thinking that I'm going to look at all once broken curves, and no matter where they break. So we often write this as union over possible breakings with a Cartesian product, but I'm going to do something else. I'm going to take the space of curves, oh goodness, hold on, the other way, from gamma minus to anywhere, maybe, no, actually, not take the compactified. And then this is going to be a fiber product with this space of curves from somewhere to gamma plus. And simply, if I have a, what do I have in here? I have a cylinder. Let's call that maybe U minus. I can look at its so there's a map to the space of periodic orbits of my Hamiltonian. And this is the fiber product over these two maps, where here I map the cylinders to their limit at plus infinity, and these guys are mapped to their limit at minus infinity. Right, notice I have equivalence classes here up to shift, but since I'm going to minus infinity, it doesn't matter which equivalence class I chose. And so this is a way of saying, really, what this consists of is a, orbit from gamma minus to someplace. That's my U minus here. U plus, and they just need to, meet at the same periodic orbit. So that's a discrete fiber product, so that's not so bad, right? So I could also write this just as a union over all the gammas in my periodic orbits, and then take m gamma minus gamma times m gamma plus. And so here we also see where then the local Fredholm description comes from, because these moduli spaces are ones where I'm actually just looking at holomorphic cylinders in this case, and I quotient by the automorphism group, which in this case is R.
So you're assuming that the set of periodic orbits is in fact a discrete space?
Finite, yes, yeah. So I should assume here that I have a regular Hamiltonian. I could do the same thing anyways, but then this might not be a Banach manifold. I mean, it's not going to completely wrong. This is not going to have a local description as 0 sets of a Fredholm section. Right? But as is, this works. I'm just going to need to use local slices to this R action. All right, so that's this case as a warm-up. That's the case that really we're going to deal with, but just so you see the real fiber product turning up here. So right, so usually when I just write curly M without an M, a bar, this is what I mean. I mean the quotient of maps modulo automorphisms, so smooth curves. All right, so this is now a curve that sort of we add in the Gromov compactification of the pseudoholomorphic curves with one mark point, or the pseudoholomorphic spheres with one mark point. So now, I don't quite know where that node is going to be. That can be anywhere in my symplectic manifold. So I need to actually make a fiber product over M to make sure that's the right place. And the way I do this is I first, maybe I call them something U minus here and U plus. So U minus is a sphere that just has one mark point at the node. So I think the notation for that was M0 genus 1 mark point, maybe of, oops, actually, wait. Here we can do something funny also. So we've probably fixed a homology class A that we want all our curves in. So the discrete part of information here will be how I split my homology class. But then once I've split that, now I need to look at the genus 0 curves with 1 mark point in that class A. Oops, A minus. Oops. And then the U plus is also going to be genus 0, but that has 2 mark points. Homology class A plus, same J. And there are evaluation maps. This only has one evaluation map. And here I need to pick the right evaluation map of 1. So maybe at the first mark point. So that's a fiber product of 0 sets of a D-bar operator, one automorphism. Well, as long as the splittings are finite, let's forget about those. Why is this still sort of locally a Fredholm problem here? Mainly because the evaluation, now I should make sure that the evaluation maps are smooth. And then M is finite dimensional. So so locally this should be the 0 set of some section where the section takes U minus and U plus, any spheres in these two, in the spaces of maps associated to those two, and I'm going to solve for a lot of D-bar equations, so I'm going to need U minus to be holomorphic, I'm going to need U plus to be holomorphic, and then I want these two evaluation maps to be the same. And let me just think of M locally as Cn so I can subtract.
So you're not going to have smoothness unless these evaluation maps happen to be transverse where you take this manifold, right?
Well, so let's see. This is going to be a map just from spaces of maps, right? So not necessarily holomorphic maps. And the transversality is not the issue here, right? Transversality would be the question of whether if these evaluation maps were transferred to each other and those moduli spaces were smooth, then the fiber product would be smooth, right? But that's not actually what I'm asking here. I'm just asking, can I describe this set here locally as the zero set of a Fredholm operator? And so essentially this here should be that Fredholm operator. So where, well, a Fredholm section in a bundle. So the hope would be, so the Cauchy-Riemann operator should be Fredholm. And then I have to worry about the evaluation maps being smooth. I mean, the evaluation maps are just extra maps into something finite dimensional. So if it was Fredholm before, I'm adding something finite dimensional, it's going to stay Fredholm. But I need to worry about smoothness here. And essentially, sort of the executive summary is that that's okay if the marked point is fixed. And otherwise it's not okay. Because P1 times a Banach space of maps to M, if I allow the mark point to vary, then this map is only about as differentiable as the maps U are differentiable. Right? So if B embeds into CL, then this map here is CL. As you can imagine, right? Because if you vary in direction of Z, you're going to pick up a derivative of U. So, it might not be the zero set of a smooth Fredholm section, but just of a CL Fredholm section. You'd think that that shouldn't be a problem until you get to a place where maybe you want to apply a Sartre-Smale theorem. And then Sartre-Smale tells you you'd better have more differentiability than you had index. Right? And so then, before you start your whole setup, you need to know how large a moduli space you're going to have to deal with later on in order to, or how much index you're going to have to deal with to, fix this. CLs. Just make your choice of Banach spaces there. It would then also raises the interesting question of, well, are there different smooth structures on my moduli spaces? Are there different regularizations in the end depending on what Banach completions I chose? So, it gets peskily subtle right there. So,
So the splitting in the second fiber product is automatically finite, right? Just in this 2P1 example.
Oh, this here, yeah. Oh God, algebraic topology. Yes. By Gromov compactness, there are only finitely many that are possible. Right. Yes. Good. Okay. Good. Excellent remark. Good. Right. If it wasn't finite, then, sort of different splittings into different homology classes you'd think are sort of somewhat separated topologically in your moduli space. So if I have a different splitting, those should not, if I like one nodal curve with one splitting, another nodal curve with another splitting, you'd think that they're not going to be, that you should be able to separate those two strata. They won't actually touch, and so locally you should still be able to do this. All right, so well, fortunately we're going to deal with Hamiltonian Floer theory, where evaluation maps. Well, you also want to worry a little bit about is my map to the limit at infinity actually smooth? Yeah. In this case, because the set of periodic orbits is finite, it's going to be pretty hard to construct a map there that's not smooth. But in general, if you wanted to do like a more spot theory where you had a manifold of periodic orbits, lots of fun worries can be had.
So as a takeaway from this, that in the broken curve case, your presentation of fiber products is regular as you want it, but in the nodal curve case, you can write it locally as some zero section of something, or the intersection of the zero section of something, but that something might not be regular.
Well, this might not be regular here. I haven't said that my my d-bar operator cuts out anything transversely. Right? So that's sort of the.
But so there you push all the regularity and somehow like a problem about J, whereas in the bottom.
I have some extra problems. Yeah, but I guess right. I mean that's also something I discussed a little bit last week. Is that you can't in general expect J to solve this problem for you, and because that's asking for an equivariant transverse perturbation,
right?
And they don't always exist.
So
So really, there's the whole sort of. I'm going to discuss the geometric regularization at some point, which sort of goes as finding equivariant transverse perturbations. And for now, my sort of direction of argument is more, what structure do we have so we can start doing an abstract description of a moduli space, in terms of some kind of section, as a zero set of a section, for which we can then have an abstract regularization theorem.
Right.
So, sorry, Nate.
I was just going to check that the difference you guys are mentioning between the first problem and the second problem is that in the second problem, the evaluation maps are mapping to this, positive dimensional manifold.
Right.
So you have to, if you want. Okay.
If these were cut out transversely, then you'd need more transversality to get the rest right. But we're not actually talking about transversality. I know a lot of you are thinking about that, but right now I'm just talking about descriptions as Fredholm problems. So good. So that's one way that we can sort of understand what the broken and nodal curves are, and sort of going towards the topology. Really, I'm going to want to say in what sense a non-broken cylinder converges to a broken cylinder, right? And so here I've also tried to be a little more precise with, marking what's really happening, right? So there's a cylinder here and a second cylinder. Those are the domains sigma, and then there's maps U minus and U plus, which map to the sort of geometrically distinct flow lines, which meet at that periodic orbit. And so I'm going to want to say in what sense a single map or a sequence of single maps you knew from a single cylinder converges to this pair of maps from two cylinders. Right? So clearly there's something non-trivial to be said here. And so we say that this is so if we find sequences, let's call them S nu plus and minus. Well, S nu, actually, that's I'm going to want S nu plus to usually be bigger than S nu minus. So both of them in the reals. Those will be shifts of my maps. So that u nu, if I shift the parameterization to center it at S nu plus, that with nu going to infinity should converge to u plus. And same thing if I take the shift by S minus, I should converge to u minus. Right, breaking, I mean, so this could be right, and I do want the difference between the two to go to infinity. Right, so there's sort of two different shifts, and you could imagine if you just look at this cylinder, like parameterized as given, it might be a cylinder that sort of maps, a big compact part. It goes to the area where it's very close to the periodic orbit, so it's essentially constant. So your entire cylinder could actually converge C infinity log to the constant periodic orbit here. So that would not be part of what we're taking here. We only want the positive energy parts. And so in order to, so clearly if all of that cylinder converges to that periodic orbit, then there needs to be, the energy needs to go someplace, let's say, right? So since I should fix my energy here. So in this case, some energy runs off towards minus infinity, some runs off towards plus infinity on the domain. And what we're doing here is we're shifting that energy back within sight to capture the geometry. And then there's also the question, how do you tell that that's actually all that happened? Shouldn't there be more parts? One way of saying it, well, no, actually. The stronger way of saying it is to say that the limit captures the entire energy. And if we have that, then we actually also know that the image Gromov-Hausdorff converges to the union of images.
The union of energies, you mean the sum of them?
The sum? Oh, sorry, yes. Good call. Union in the reals, yeah. Probably. Said theoretically, that's what I meant. Yeah. Good. Right. So different shifts, giving me the two different limits. And that's pretty similar to the way that I think I defined Gromov convergence of a parameterized spheres to a bubble tree before. So let me just sort of remind you here. Here it's a little bit complicated. So last semester we had one main component. Here it's not really totally clear which one should be the main component. Maybe the one that contains my marked point. But to be similar to this, I could say that there's two sequences of Möbius transformations. So that one reparameterization converges to U plus, and the other converges to U minus. And again, I would like the energy to be preserved. Which then implies something very similar to the Gromov-Hausdorff convergence. Right. I was a little bit sloppy about what kind of convergence I mean. Here, really what's happening is that these maps will capture all this part above, and the energy that sits here will concentrate to a single point for those maps. So what's going to happen here is that this is going to be a C infinity log convergence on P1 minus the point that's going to become the node. Right? And so in one reparameterization you see energy concentrating at one point, and then we do this sort of rescaling at that bubbling point to sort of see what's happening at that bubbling point. But in rescaling, since we have spheres, we might as well extend that to the whole automorphism group. So we're sort of smushing the entire bubble that we saw here into a point, and then in rescaling we're going to see this extra component. So this is all not super precise. So here at least I can also say C infinity log. Since I'm not looking at sphere bubbling here, sort of the places where convergence fails is just at plus minus infinity. So, right, and really, strictly speaking, I should make sure that my marked point here is somewhere compatible with this whole endeavor. My marked point should somehow converge to that marked point. So that's the first sense of what this topology is supposed to do for us. And so now, to get into the gluing language, there's going to be two steps. The first one is something called pregluing, which is a fairly soft construction. And we're going to use that to actually make a topology on this moduli space, on this compactified moduli space, in which this is the notion of convergence. So in which a sequence, a sort of Gromov convergent sequence like this, actually converges to this broken guy, in the topology. And the gluing construction then is going to construct some type of generalized smooth structure near the broken curves, but smooth structure that actually lives on open sets within M bar. So they're going to have to sort of contain broken curves and non-broken curves. And by smooth structure, well, what do I mean? If this guy was smooth already because maybe we had a regular J, then we would like to actually make the compactified moduli space also a smooth manifold or orbifold. So that's the traditional smooth structure, and that's the gluing construction I'm going to discuss for now. But really later on there's going to be a lot of similar constructions where we'll have weakened the notion of a smooth structure. But we'll still want to do gluing to get that description near the broken ones.
Are you saying plus marked point contribution, is that word? Or?
Yeah, or marked point condition. right? So there should be a u nu. Well, no, I don't really want to say what that. This is also wrong. This is not u of infinity. This is u nu of infinity. And really, I should mark my points infinity on my spheres here. And so what I would need to say here is that the minus part reparameterized, well, I'm going to have to hit the infinity point with the reparameterization, and it should converge to the infinity point. So probably my condition here is that psi nu minus should fix infinity. Psi nu minus is going to fix infinity, and psi nu plus is going to push this infinity point to the node. So that's sort of the subtleties that I'm going to keep pushing under the rug. It's good for you to ask, and I'm just going to try to tell you that this is a subtlety you should worry about at this point, or this is a subtlety you shouldn't worry about. Because I'm trying to get sort of to the analytic juice of these things. So, right, so more pictorially, right, I want to make a topology on my compactified space. So, and that means I need to say what the open neighborhoods of a broken thing are. And in what sense does it mean that, you know, a non-broken one here is an orange point in a green neighborhood of this red broken one? So in the Fleur sense, the broken ones actually are going to be boundaries of the moduli space. In the Gromov-Witten world, the nodal curves in some sense really sit in the interior of my moduli space, so there should be open sets so that non-nodal ones somehow can be in that neighborhood. All right. And the way we're going to do this is we're going to take a fiber product, namely exactly, so now these represent broken or nodal curves. And then there's going to be some gluing parameters, finite dimensional extra data, and from that we would like to make new holomorphic curves from that. We can't quite, our pregluing is going to give us sort of maps that are close to holomorphic. So, by almost, I mean here sort of d bar j will be small. And then sort of the preview is that from here we're going to sort of project back to the space of actual holomorphic curves, M bar.
So what goes wrong in this process so this fiber product consists of things that are only holomorphic, right?
Right.
And then
yeah, well, I haven't written it down. So let me write it down and we'll see what goes wrong. I want to say one thing here. So usually when I I'm going to always take my gluing parameters to contain 0. And I want to think of 0 as the parameter that says we don't glue. So if I have a pair q minus q plus 0, I would just like to map that to the broken one. So that just says that, so that I'm trying to make a neighborhood here, maybe not an M bar in some bigger space, and I'd better make sure that the broken one actually sits in that neighborhood. So, and from 0, I'm going to hit that. Right.
The gluing parameters is going to be non-negative real numbers, or?
Well, so okay, yeah. So let me say something.
There are going to be sections of the nodal bundles to actually do it 90.
Ooh, yeah. Well, no. That you would need if you did sort of funky gluing, you know, and a sort of bad neighborhood of you know, non-transverse intersection things. Let's see. In this case here of nodes, the gluing parameters here are actually just simply going to be small disks in C. So they're going to be sort of, what do I write this? E to the minus r plus I theta well, yeah. R is going to, well, actually R can be 0. Oh no, R, no, I don't want that. So, because of my minus R here, I'm actually, so I want this to be a small disk. In C. So I'm going to take theta between 0 and 2 pi. And R is going to be, well, some large number up to and including sort of infinity, where, you know, if little r is equal to infinity, I'm thinking of this as simply equal to 0 no matter what my angle is. And so these this little disk will be, you know, I can think of lines all meeting at the origin, so that's 0. And so if this was an isolated nodal curve, you know, that's pretty much the image that I want to have. So I want, in that case, there is sort of no dimension coming from here, and so, you know, all the interesting information, I just have an isolated point here. So I have a little disk that should map into my moduli space eventually, and yeah, that should simply be its image.
In this normal bundle comment was that sometimes you might be gluing in something that doesn't have a trivializable normal bundle, or
no.
We can ignore
No,
that.
that's really just so.
I mean, that's going to rise.
Let's see.
Here
That's going to rise.
in the
First of
example
all,
with the broken cylinders.
only if your broken cylinder, only if you break, and you either have a more spot situation at the ends, or you have non-transversality. I think that's non-transversality, right?
Yeah.
What you're thinking is gluing gluing branched covers of cylinders in, which we're totally not doing here. So that's a situation that's sort of, how should I say this? In some cases, you can deal with lack of transversality by doing a more fancy gluing. But we're not talking about transversality, so no. The basic gluing ideas are the same.
Sorry, maybe
Yeah.
I misunderstood what you guys were talking about. But when you said normal bundle, I thought what you're talking about is that when you're doing the gluing, you say near the nodal point, you're going to write your maps as x of some section of.
No. That, I'm
And
about to
added
do
the
that.
sections,
That's
so
not no.
that's not
Normal.
what you're
That
talking
was normal bundle to. That was like an obstruction bundle, or yeah. I think, right?
Yes.
So yeah, but no.
Those are glued.
Strike this. It's like that's fancy gluing that sort of solves particular problems in a particular setting of contact homology. And yeah, I could make, you know, sort of twists and turns to try and fit that into this discussion, but you know, not before I've actually done sort of the basic discussion. Right. So in this case, this is kind of actually a bad picture here. Here I want to, in the flow trajectory gluing, my gluing parameters, will be usually a little open interval. Where now I can translate this little epsilon into a large number, maybe e to the minus capital R. And so then again, 0 means not gluing at all. So yeah, this line here, in the image, well, I should maybe do the green line. So not gluing at all would be this point, and then gluing a little bit will get me into the interior. And so here, in this picture there should be a one-dimensional family of broken guys, so I can actually get everything. So in this case this would be one-dimensional. So in those two examples, that's what we're expecting. So you can see here, right, so the question of whether there's boundary or no boundary is actually something that you can see on the level of gluing parameters. So here the gluing parameters have boundary at 0, and the thing is that when you glue nodal curves, you have a complex gluing parameter, and there 0 is just not a boundary. Good, but still, what is this that I'm doing here? So for this, together with a gluing parameter, so in this case my gluing parameters will be between 0 and epsilon, and we're just going to identify this with open set, I guess, e to the minus some r0 up to infinity. Somewhat sloppy notation, right? So 0 corresponds to infinity. Oh, gee, that's silly. I want to identify it with r0 to infinity because I'm going to write epsilon as e to the minus r0. Okay, so now, given a pair u minus u plus and a gluing parameter in here, I need to tell you what the gluing, what this pre-gluing map does is it takes a tuple and makes a what we call pre-glued cylinder. So that should now be a single cylinder. At least if r is less than infinity. Right, so if r is infinity, then it just does nothing. It just keeps the pair. That was in the previous slide. So if r is less than infinity, I need to define this map. Let me call this b sub r, and so now let's see. I would like to make a picture of my domain. And say what b sub r should look like. So the way we're going to do this is we're going to take the top part of u plus up to almost the periodic orbit, and we're going to take the bottom part of the U minus also up to almost the periodic orbit, and then we're just going to have to fudge in between. So that's where something. Yeah, because we want
originally
to.
when I made my comment, I never meant to. Yeah, no, I mean you're right about your point. I shouldn't have brought up normal bundles, but I didn't mean to.
Yeah.
I meant to say cutoff functions. And
Cutoff functions. Okay,
and
yes, there will be
instead
cutoff
speed out sections
functions.
of normal bundles. But no,
Yes.
I meant
Yeah. Good. Okay. Yes, there will be cutoff functions here. So. Right. So, on a large part here, I'm just going to define VR by U plus. On another large part, that's just going to be U minus. And there's going to be some part here that's on which I need to interpolate. So, what's going to happen in formulas is, and now you can pick and choose a little bit how you'd like to parameterize this. I usually like to think of 0 somewhere really properly here, and then I want, right, so the U plus 0, I guess, has sort of its own 0 here, and that probably maps, well, depending on the parameterization, somewhere into the middle of the cylinder. And so now I want to sort of, have this still in my domain here, so I'm going to have to push that 0 up. So this sort of 0 is going to get focused, reparameterized here, and the 0 here I want to see somewhere far down on the domain where I have the U minus. So I should probably really write that I'm having sort of I want to think of having the sort of map modular reparameterization there, except I'm going to pick a parameterization. So in formulas, that's going to mean that if S is large, I'm going to be up here and I'm going to have U plus. But S is large and U plus got shifted up, so I'm going to have to subtract maybe R over 2 and T. So I'm going to do this for S. Oh goodness. Usually, I guess I could do bigger than 1. So there's going to be some domain here. 1 minus 1 on which the interpolation happens. Same thing, U minus gets shifted down, so that's by adding R over 2. And in the middle, I should just have a cutoff function that interpolates. So function that's plus, geez, I am head over. So 1 near minus 1 and plus 1, and 0 near plus 1. We call this, what do we usually call them? H?
Yeah.
And so that means I want to multiply U minus with H. Still the shifted one. And then multiply U plus with 1 minus H.
function U?
Yeah. Right. Good question. Indeed. So I should write now. Okay. So now is the time when we could talk about normal bundle, right? So all of this happens in a neighborhood of my periodic orbits here, and I'm going to pick sort of a neighborhood in which I'm going to trivialize. Well,
I mean, even if you don't trivialize, there's such a thing as a scaling function on the normal bundle.
Right.
So now I think what you're doing is you could think about taking x of a section of the pullback tangent bundle and then just scaling the arguments of x.
Yes. Yeah. But in this case here, what is a neighborhood of this is something like, so right, okay, apologies. Right, so I'm going to make this something that I can add in, I don't even actually, no, this guy is injective, right? It's a periodic orbit, so it has a normal bundle. Right? So, I guess, the best way to really sort of just idea-wise understand these things is to just pretend that your target manifold is Cn, because really as an addition, there's some interpolation happening, and then whether you write this as an exponential map of something interpolated, or you use a normal bundle of that's sort of differential geometric tool. That's just our language. These are the concepts. Right. So.
I see. Your claim is that this V sub r there has no reason to be J-holomorphic.
This has absolutely no reason to be J-holomorphic, indeed, right? So, U plus is holomorphic. If I shift it up, it's still J-holomorphic. U minus is still going to be J-holomorphic. But on this little, domain in between, odds are it's not going to be J-holomorphic. However, right, if I do my shifting with a very, very large parameter r, then what I'm looking at here is a domain where for U minus, I'm pretty much close to plus infinity. So for U minus, I'm in this domain here that gets mapped, almost constantly to this periodic orbit. So same for U plus, I'm sort of very near minus infinity here. So I'm going to map very close to that periodic orbit. And really, there is, both of these essentially satisfy just the periodic orbit equation, and that if they were actually constant sitting at the periodic orbit, then this interpolation would be no interpolation, and it would just be constant at the periodic orbit, and then d bar would be 0. So that's the argument why d bar of this is small. So that's the piece of good news here. I don't know whether I should add that here. That's my next slide. Yeah, no. Right, so good news here is that d bar j of that is 0. D bar j of this is also 0. And here, d bar j is small. Well, now, of course, I've cheated terribly. There should be, it's not a Hamiltonian, there's an extra Hamiltonian term in my d bar operator now. Good. Right. So, yeah, and that's right. Right. So the reason that this makes sense, and the reason that you're probably confused about normal bundles and everything, is that when I do my trivialization here, then essentially the periodic orbit should just become 0. And so, yeah, that's why I can add here. So, if both of these just sit at the periodic orbits, they're just both 0, and then the whole thing just stays in the periodic orbit. Precise formulas in every textbook, which will be less confusing, but also hopefully probably less intuitive. So, right. First sort of geometric remark is that, I shifted 1 by r over 2 up, 1 by r over 2 down, so sort of in the domain the shifted zeros are distance, capital R apart. So that's the meaning of that gluing parameter. So you shift centers, say, apart. You could have centered these so that their energy was sort of the so that the energy was centered at 0. And then we'd be shifting some energy up and some energy down. And the other remark is more an analytic remark. What happens here, right? I have a map that depends on the maps and the parameter r. And what happens in this map is that there is a reparameterization happening. So as a map from a large space of, from a Sobolev space of maps, this again is not going to be differentiable at all. The reason we don't have to worry about this is because we're just looking at our moduli spaces, which right now don't even have a smooth structure, but eventually we might imagine them as being contained in smooth maps, and having a smooth structure, and then this map here is perfectly fine. Right. So. Okay, so with that kind of map, I would now like to say something about define the topology. And that's where the weird thing comes in, where my pregluing didn't actually map to n bar. So I need to say what it means for an unbroken V to lie in an epsilon neighborhood of a broken U plus U minus. So this is my epsilon neighborhood here. Which I think I'm going to take out. And so I'm going to say that this is so, essentially reversing the statement of convergence. So I would like to say that V is close to a preglued curve. So right. So and so there's 3 parameters I can wiggle with. I can wiggle with the gluing parameter, and I can wiggle with those maps. So V minus V plus will both be maps from R times S1 to M. And I'd also like a gluing parameter. It's bigger than my lower bound R0, which in this case an epsilon neighborhood here might mean that this is ln epsilon minus ln epsilon. So that's my large number here. And so these maps here in some Sobolev topology, which I can choose here, or maybe, let's see, let me take the metric on the smooth functions. Right? Smooth functions are still a metric space, they're just not a Banach space. So just to be totally precise, I'm going to take the C infinity metric between V minus and U minus should be small. Same thing with V plus and U plus. Right, so I'm allowed to make V minus and V plus maybe not quite holomorphic. And then this wiggling should give me that, well, maybe I should say that V is the pregluing of V minus and V plus. But then I haven't allowed for some kind of shifts happening here. And so really, I should talk about the equivalence class V. And so I should just look at this mod R shifts. Right, so if now, so this sort of makes a lot more sense if you're on this whole big space of just maps, modular automorphisms. If you're also trying to think about these things being holomorphic, it gets a little confusing, right? Because V is maybe supposed to be holomorphic everywhere, but the U plus and U minus are also holomorphic, and so now I'm going to take V plus and minus that are maybe not holomorphic, but after I preglue them, they should be holomorphic again. Yeah. So clearly, there's going to be these areas where the pregluing does nothing. It's just V minus and V plus. So in those areas, V minus and V plus will simply be shifts of V, right? Which is nothing but to say, and those shifts of V need to be close to U plus and U minus, which is exactly what my definition of convergence was. So, yeah. Knowing that this pregluing outside of some very small set is either a shift of V minus or a V plus, tells me that the shifted V really is close to U pluses and U minuses. So what did I want to say here? Right, so shifts of V are V plus minus, and they are approximately equal to U plus minus. So that's exactly the convergence notion we had before. So, well, I mean, okay, so here I defined an open set, but I actually defined an epsilon ball, so this is pretty close to actually making a metric. And you might have not cared about metrizable when you saw it the first 5 times, and I don't think I ever cared, but when I tried to actually understand sort of the Kuranishi type regularization approach, the metrizability started to become really, really crucial. So one can worry about it. I'm not gonna worry about it here. But a really nice thing about metrizable spaces is also that they're definitely Hausdorff. So that gives us a topology, roughly speaking, right? But really, our big scheme, goal is to, get a smooth structure, And so, if we were successful in making, smooth structures on a non-compactified moduli spaces, then this fiber product here is not so far from a smooth structure. Gluing parameters are going to be in a finite dimensional little set. So if we now had a nice local map that's sort of maybe a homeo, we would get a nice sort of generalized smooth structure on a compactified moduli space. And so for that, the second step is, right, so the pregluing is going to get us maps whose d bar is small, and so now we want from those maps to obtain actually holomorphic maps. So this is going to be VR, and we're going to map this to, now I'm going to write X of VR. So, we're going to have to add a little correction term to make it actually holomorphic. And so these CRs here we're going to find as solutions of a Newton iteration. And so what this proposition here is what one gets from Newton iteration on Banach spaces. Particular, it's going to be a C1 map. That's going to be a D-bar operator. It's going to have a bounded right inverse. There's going to be various constants. There's going to be an approximate solution. That's going to be our VR in some sense, but really it's going to be 0, which is, it presents the VR, and then the actual solution X is going to be the CR, which is going to be close to 0. And so I guess that also means that F is not D bar of the C, it's going to be here D bar of X V of C. So that's going to be my task for Wednesday. I'm going to have this full Newton iteration on. I'm going to actually set up precisely the language, also with exponential maps, and at least give you a hunch of how to prove the estimates that you need in the game here. The one thing I would like to point out is that this is not just an implicit function theorem. People often say that the second step of gluing is just an implicit function theorem. And there's a massive difference between implicit function theorems and Newton iteration. Implicit function theorems work on Banach manifolds, and Newton iteration with this precise relation of constants only works on linear spaces. So be careful what you quote there. So this comes from McDuff-Solomon book.
So kind of, is this, to me, this is kind of like a contraction map.
Yeah, that's exactly a contraction mapping principle, right? Yeah. So there's just going to be some subtle relationship between constants that, and we'll discuss a little bit of how you can actually make the constants, happen to fit in the gluing. But contraction mapping principles only work on Banach spaces.